All right, hi everyone. So for this screencast, what you're going to want to do is you're going to need to have these notes that I asked you to print out. All right, it's in my hand right here. And what I want to talk about here is a particular differential equation that you are going to absolutely need the shortcut for, because you are not ever going to want to do what I did here. All right. And let me just emphasize here what this differential equation looks like. The differential equation that I'm talking about here will always have this form. And this form is right here. This dp by dt equals some constant times p times 1 minus p over 240. Here is the general right here. All right. And if you look at this, it's the differential equation. It's some constant times y, right? Or wherever this is. It's not always going to be p, right? It's some constant times the dependent variable times 1 minus that in dependent variable over another constant a. So what's important to know here is that in this differential equation form, when you see this differential equation, the differential equation will always have this form where k and a are constants. Okay, let me just take you through, if we were going to do this longhand, let me just take you through the steps here. This is something that I don't ever want to see you doing because it will just take so much time. If you look here in step 1, all I did was I did some multiplication. Or no, I did some factoring, right? And then I just did some cleaning up here, 240 divided by 5. And then I separated the variables here. And if you look at this side of the diffie-q right here, right, when I separate the variables, you're going to have to use partial fractions. Believe it or not, I actually did that on a separate piece of paper. So you can just imagine the amount of pencil lead required to solve this diffie-q. When you use partial fractions and you decompose, this is what you get in step 4, right? And then when you integrate, look what happens. Here's what happens when you integrate, all right? And again, I left out a lot of work here just because it started to get just incredibly dense. But the point is, as I'm hoping you're seeing, is that after I solved for C, because here, what was there? Was a point? Wait, was there a point that was given to you? How did I solve for C? I solved for C because, oh, you know what? There was the point, I think. One thing that I didn't write down here is that in this logistics growth equation, this was the case, and there was some given point. The given point may have been, I think, 0, 150, possibly, I think it was. Yeah, so I just didn't write that down. So after I used that point 0, 150, and I solved for C, and after a lot of algebra, this is what I get here. Okay, P equals 400 all over 5/3 plus e to the negative 5t. And this kind of function, this is a major blast from the past. This is called a logistics growth function. And Oliver, do you remember when you asked about uninhibited growth versus inhibited growth? You're going to see that for a logistics growth function, this is inhibited growth. And you're going to see why in just a moment. Okay? So what you see here is when I graphed this function, for a logistics growth function, there are a couple of criteria. There's a couple of graphical features that are unique. There are 2 horizontal asymptotes. How did I get this upper asymptote here? This upper asymptote is the result of me asking this question, the limit as t approaches positive infinity of that p function, which is 400 all over 5/3 e to the, plus e to the negative 5t, okay? And as t approaches positive infinity, e to the negative 5t approaches 0, and 400 over 5/3 equals 240, all right? So this is the upper asymptote, p equals 240. Here's that point 0, 150 I was talking about. I'll talk about this green point 120 in a moment. This lower asymptote at p equals 0 is the result of the limit as t approaches negative infinity of that p function, 400 over 5/3 plus e to the negative 5t. Okay, and this is going to equal 0 because as t approaches negative infinity, e to the negative 5t approaches positive infinity, so you have 400 divided by an increasingly large number. This will all approach 0, hence the lower asymptote. All right? The important thing to understand is that when you have a differential equation that is in this form right here, okay, that is in this form, and here's where you're going to just want to memorize it. If you see a diffie-q in this form, you're going to want to know that this is a logistics growth function with the following criteria, the following features. Whatever this a value is, okay, this a value right here, whatever that a value is, that is the upper asymptote. I should say the upper horizontal asymptote, okay? So notice at the very end, when you look at this, right, the upper asymptote is 240. Look at the original diffie-q. Do you see here? This was 240, all right? Oliver, this is inhibited growth because if you look at this function, while we do have growth, the growth is inhibited or it's bounded. There is never a time when this function is going to increase beyond 240. Okay? All right. The other thing is this. You are almost never, ever going to be asked to solve a differential equation that looks like this. You will be asked questions like, and this is where we're going to turn to the next a few pages in your packet here. And it's the packet. And ladies and gentlemen, when I ask you to print something out and have it and to kind of staple it in the order, it really behooves you to do that and keep it in some organized fashion so you don't have kind of a disastrous mess happening, all right? You're going to want to be able to notice a couple of things. You want to recognize when a differential equation is in this logistics growth function form. You're also going to want to recognize how to manipulate it because this is the kind of form you want to get it into so you can find A, okay? The other critical feature too is that once you see the upper asymptote, at y equals half of A, dp by dt is greatest. What that means is, okay, at right here, because 240, half of 240 is 120. At y equals 120, at this point, dp by dt is greatest. What that means is the slope of the line tangent to the p function is greatest. What that also means then is at that point when y equals 120 or when y equals half of this upper bound, that at that point is a point of inflection. Okay, that's what I'm saying here. All right. So that's what I'm telling you here in this screencast. I want you to see, to show you a new diffie-q, to show you that while you could solve it out, you're never going to need to do that. And not only will you never need to, you are never going to want to because it's just long and arduous. But here are the shortcuts. Go now with me to this question in your packet, and I think it's right here. It is okay, it's not this one, pardon me, just come with me here. It is the 2004 BC question 5. Where is it? It's here somewhere. Here we go, all right? So if you look at this, right, a population is modeled by a function p that satisfies the logistic differential equation. So this means the same thing as logistic growth function. That word logistic is kind of a giveaway. Logistic differential equation. The logistic differential equation is referring to this particular differential equation. You know that a logistic differential equation will then therefore describe a logistic growth function. Okay, so the fact that they actually told you it's a logistic differential equation is very nice. You'll notice here that if you look at this, they already put it in the form for you. Look what's happening, right? The general form for a logistic differential equation is dy by dt is equal to some constant times y times 1 minus y over some constant, right? And if I look at this here, it's very clear to me that the constant A is 12, okay, and K here is going to be 1/5. So we need to be careful. It's not 5, it's 1/5, okay? Now look at this question. If the initial value of P is 3, what is the limit as t approaches positive infinity of p of t? If p of 0 equals 20, what is the limit as t approaches positive infinity of p of t? What they're trying to tempt you into doing here is they're trying to tempt you into solving this differential equation, inputting in the value to find the constant, and then taking the limit. But you know that if this is a logistic differential equation and you see that this value here is A, in both of these cases, the upper horizontal asymptote, right, P equals 12 is the upper horizontal asymptote. In other words, for a logistic differential function, a logistic differential equation, a logistic growth function, the initial value doesn't change the upper horizontal asymptote. Okay, so really in this case, we know that the limit as t approaches positive infinity of p of t in both cases is positive 12. Hi, honey, how are you?
Hi.
How was school today? Go ahead, go wash your hands and get a snack, okay? Okay. And here we go. Here's another part B. Part B is, again, it's really testing whether you recognize the significance of the logistic diffeq. If the initial value is 3, for what value of P is the population growing the fastest? Hi, honey. Do you want to say hi to my class? This is my son, Justin. Say hi.
Hello.
Hello. Go ahead, wash your hands and get a snack. You know that the slope of the line tangent, you know that dp by dt is going to be greatest at half of that value, at 1/2, at 1/2 of 12, right? So at 1/2 of 12, you know that it's going to be growing the fastest. If p of 0, for what value of p is the population growing the fastest? They're only asking for the y coordinate of the point, so at p equals 6, dp by dt is max. Okay, let's come on down to part C. A different population is modeled by a function right here that satisfies the separable differential equation. Okay, now this one, again, you have to be very, very careful. This is not a logistic differential equation. Do you see why? It's dy dt equals 1/5 times y. That looks similar, but look over here. The fact that this is not y and that's an x or a t, so to speak, means something different, all right? So the part of this is making sure you keep track of what's a logistic differential equation and what's not. Okay, go ahead, find y of t if y of 0 equals 3, and then for that function y, find this limit. Go ahead and do that and then check back with me. Okay, so here it is. Here is me separating out the variables. Notice how I just kept the 1/5 with the t side of things, okay? Knowing full well I could see kind of ahead that I'm going to have ln y here, so I might as well keep everything else to the right because I'm going to exponentiate right here, right? And you'll see how I automatically made the times e to the c. I just made it a constant k. I used this point, 0, 3, and I solve for k, and here's the function. Notice again, this is not a logistic growth function because this was never a logistic differential equation, okay? The limit as t approaches infinity, so this is important, as t approaches positive infinity, notice the exponent of e. As t approaches positive infinity, the exponent of e will approach negative infinity. E raised to negative infinity is going to approach 0, so 3 times 0 will approach 0 right here. Okay, so for homework, here's what I'd like you to do. I would like you to do there's a bird question right here, this one. Please find it, the bird question, and then there is this question right here. Okay, the bird question, the 1998 one we did in class already, but then there's this one. So the bird question and this one, 2001 AB6. They are all in your DiffyQs packet. Once you finish the bird question and the that last question, that makes this differential equations packet, I believe we finish it completely, all right? The other thing too that I'd like you to do is if you go to your notes that I gave out for this day, do you remember how I printed out notes? I would like you to also do the notes It says it starts with logistic models. There are 2 pages there. All right. I'd like you to do that as well. So once again, the homework is to do the questions I referenced in this packet, and then to go to your notes packet and finish those questions on the pages that refer to logistic models. Have a great weekend, and I'll see you Tuesday.